every time the P is changed to C, this is called a context switch. This was the code that we were looking at last time, and one thing that I want you guys to pay attention to is that why do we have different processes, and is it possible to run parent process and the child process in parallel with respect to each other? I have written a loop here which runs for a very long timeline, like 100,000 times. And there is another loop here which also runs for 100,000 times. This loop prints a C every time it executes, because this is from the child process. And whenever this loop executes, it is from the parent process, so it prints a P. I have written a wait instruction here, which waits for the child to finish execution, and this is, waits unconditionally, right? And that fact is, shown with the null. So someone could say, what is this null that you have written inside the wait command? That null simply says that the wait that the parent is doing for the child process is unconditional, right? Null represents, or it tells the OS that we want the parent process wants to wait for the child process unconditionally, that it wants the child process to finish execution in every way possible, and only then the parent process will continue, right? And by the way, the child process does not finish over here. Child process is going to continue to this line and this part. You should be mindful of the fact that the child process is not finishing over here, finishing its execution. It is going to this line and then finishing execution, because so both the processes are going to go through these lines of code as well, right? So okay, so I was saying that the parent process has written the wait instruction or the wait command so that it waits for the child process to finish execution, and until it finishes execution, it waits at this line, and it cannot continue until all of these lines are executed, right? So here again, as I told you, that 100,000 C's are printed by child process, 100,000 P processes are printed by the parent process. If the parent process is unable to wait for the child process, then there should be some mixing of C's and P's that we would see, we should be able to, see in the output. Okay, so I'm going to try to scroll up. So now let's see if we are able to see any mixing of P's or C's. So I'm trying to find that. So these are all the P's. There is no C I can see here. No C present, no C present, no C present. So as soon as the P's end over here, or they were beginning from here, I can see that C's are printed at this the other location. So I'm going to see again for inside all the C's, where if I can find a P inside any of the C's. So I'm unable to find any of the P's here. That means C's and P's were run absolutely independent of each other. The parent process waited for the child process to finish execution, so all the C's were printed. Now, let me get rid of this line, which is the wait line, which means that I'm telling my program to for the parent process to not wait for the child process. In other words, now I'm raising a possibility that the parent process can run in parallel to the child process. Now let's see if we are able to see an evidence for that. And let's see. So okay, so let's scroll up now. Here you can see there are actually quite a lot of different instances of that, but let's look at this part. So here you can see that C's and P's are mixed together. Here also you can see C's, and so there is a lot of mix up. Every time the P is changed to C, as you see here, this is called a context switch. That the parent process was taken out from the CPU by the operating system, and child process was sent into the CPU by the operating system. Similarly, there is also a context switch over here. When the C changes to P, that means the child process was taken out of the CPU and parent process was put inside the CPU by the operating system. So this is an evidence to our understanding, right? Similarly, when we wrote this loop, we never thought earlier than this point. Whenever we write a line of code in a single program, we never expect that line to be interrupted by anything in a normal circumstance. But since now we are actually running two different processes, and we're able to see the output of both the processes on the screen at the same time in the same context. So we were expecting that if we write one loop, even though, or no matter how long that loop is, how many iterations there are, that loop should never be interrupted by anything. And we are absolutely right for the single program. If we talk about a single program, nothing from the same program would be able to interrupt this loop. Similarly, nothing from this program would be able to interrupt this loop, and it should not be able to, and it does not interrupt that. But there is no constraint of this code interrupting this code, or this code interrupting this code. Why? Because both the codes are from different separate processes. One is from the parent process and the other is from the child process. So this is the point that I'm trying to make. I'm trying to re-emphasize on it again and again, that both of these codes are from independent processes, even though they're related to each other with parent-child relationship. Now, once the child is born, both the processes are absolutely independent of each other. There is no working relationship between the two. They are going to work independently from each other. And that is the reason why this loop was executing, and operating system only gives a limited amount of time to a process to go into the CPU, right? So this loop was happily executing while this process is unaware of the fact that the operating system has given this process or the child process a limited amount of time to go into the CPU, right? Similarly, this process, whenever it goes into the CPU, it is also given a limited amount of time to stay inside the CPU by the operating system, right? So that is why we see a context switch. As soon as the time given to the child process to execute in CPU is over, the operating system brings in the parent process into the CPU so that its code can be executed. That's why we are seeing a switching between, sometimes the parent process is running, and then for a while the child process is running, and then for a while the parent process is running, and then for a while child process is running. No matter how well we know what is going on, we cannot predict for how long a process stays inside the CPU, because so many external parameters are affecting the decision making of how long a process will stay in the CPU. So here you see the parent process stayed inside the CPU for a short amount of time while the child process stayed for a longer amount of time, right? Similarly, here you can see that the parent process stayed inside the CPU for an even very long time, like all of this time. And then the child process stayed in the CPU for an average amount of time, right? So these are all the context switchings which are happening. We can see with our own eyes. It's an evidence to the concept that we built earlier, that multiple processes are independent of each other, and the operating system switches the context between those processes to improve the user experience. Because if the operating system was to simply focus on these 100,000 lines and to simply show the output for these, the user of the parent process will get annoyed and frustrated that my program is never running, right? But since the operating system, without the knowledge of the child process, without letting the child process know that this thing is happening, it gave some chance to the parent process to be run on the CPU. So that's why both the programs thought that, okay, well, I am running and I am also running. This parent said, I am also running. The child said, I am also running. So both of them, for 100,000 lines, multiple times both of these processes got the chance to run on the CPU and say that, okay, I am executing as well, I am executing as well, right? Context switching is the same across the board, no change. The reason to that is that no matter which language you use to write a program, every single program in your computer is going to be translated or compiled, or in the case of some languages, simply translated into binary language, and then it is going to be run, right? This is the point that I am going to make. I am going to build on top of this concept that it is really inefficient to do this if you're trying to make use of multi-core programming or multi-processing or multitasking, whatever you say. If you're making trying to make use of that using different processes, it is really inefficient. Why? Because operating system will get burdenized if you put in multiple processes for every little thing that you think of that you want to run in your program or in your solution to your problem, because we write programs to solve problems, right? So if you have solved a problem using a program, you want to divide that program into different processes in order to make use of parallelism. It is a very inefficient thing to do because processes take more time in memory to create. Now, we have a solution to all of this, and the solution to this is that we don't create different processes in order to make use of parallelism. Instead, in a single program, we make multiple threads.